Hello, everyone. Um, Today I'm here to present to you my paper for the conference of IEEE Symposium on Computer Applications and Industrial Electronics 2025. My paper title is Batch-Based and Non-Batch-Based Input Comparison into Deep Learning Models, Application for the Segmentation of Retinal Diseases on Optical Coherence Tomography Volumes. This paper is presented by me, Khaled Al-Saih, which I currently work as a researcher in University Clermont-Auvergne in France, with my co-authors Dr. Faris Al-Sharji, who works in USA, and Dr. Muhammad Isam in Iraq, and Dr. Rihan in Saudi. Four of us, we collaborated to do this work, which is an extension to my PhD work, in which we compare the input and we use three familiar deep learning models. But the idea is just to see the impact of the input either in full or in batch, either in 2 dimensions or 3 dimensions or 2.5D dimensions. We will have introduction, methodology, and experiments and results, conclusion, and future work. For the background and motivation, we have an importance given to the human vision. In fact, if vision is disturbed, we cannot see really clear, and this would impact our decisions for daily life activities. And for retinal diseases, could lead to vision blurring or loss. Um, we have the diabetes is one of the factors that could affect the retina and eventually would affect the vision. Um, the two diseases that we are gonna really study, they are like the diabetic macular edema and the age-related macular degeneration. Uh, for the age-related macular degeneration, it's caused by getting old, obesity and smoking, and that's why the name is called age-related. And then States usually spend 4.6 billions for direct healthcare per annum. That's in general. And for AMD in USA, there are like 11 million people affected by that, so it's quite a big number. And this figure is anticipated to be doubled by 2050. Um, so the idea of having some images for this number and requires a lot of manpower. So imagine when this exists at China or India, which are a huge population, the graders number is small for just verifying at each image, and this time taken process to identify where are these. We will see in some images that the disease is really could locate in a small thing, and the disagreement is huge. This is an example of the dataset that we used, which called the Retouch Challenge dataset. It provided three scanners called Cyrus, Spectralis, and Turcon. We can see here, like this is assist. You see how small it is. This is really small. So this could also exist from disagreement between the graders or the people who they do the ground truth, the experts or the ophthalmologists, and this is really difficult for them. And imagine for us, like when we want to establish an algorithm that could say it all. And then we have three fluids which this data set tackles, namely intraretinal fluid and subretinal fluid and the pigment detachment. So for the yellow is the IRF, and for the dark blue is the SRF, and the PED, which is the light blue. And we can see that the images are not the same, but you need to know that are the original images, not denoised. And this study is more focused about the performance rather than the results, the actual results. The dataset size, we can see that it comes into volumes. It's not a grayscale image, like what I mean, it's not a 1D image or 3D image, but rather than that, it's a volume, which is in 128 images for Cyrus, 49 for Spectralis, and 128 for NIDEC and Topcoin. What was provided in the challenge is the training dataset, and the testing, it was left for the organizers of the challenge. So what we did, we used these images alone. We trained each scanner alone in another papers of mine, which you can see that I tried to train them all together, and I have tried various experiments, extensive studies around these data sets, in which we take around 70% of them for training and the rest for testing. Some related work to that, we can see that we have around 5 papers from the contributor to the challenge that they use 2D input, and then you have 2.5D input was used by 2 papers, and 1 paper utilizes the 3D input. And then the results that they obtained so far, it was not good enough to make it an application, or like to depend on it at least, because the human performance, it was 83%. So nobody really that have tried to exceed the human performance so far. What we have made use to study is like the 3 familiar, we can say, architectures, namely UNet, Deep Lab V3, and SIGNET. Um, as you can see here, there are 1, 2, 3, and 4 layers, and we know UNet was first released for medical application. They have used also the patch. Before now, there are a lot of extensive work in UNet. It's the most cited paper for segmentation, as I believe. And then we have Deep Lab. It's a very good architecture which use the atrus convolution. And then you have the SIGNET, which use the same as the UNet, but instead of transferring the whole image, it just transferred the, we can say, the max pooling indices, which save time and the calculation. So to give you an insight about the input to the sizes, like the input to the full image of 2D, it's 572 by 572 by 1. It's all resized. The images are all resized. 2.5D and 3D, full image size is 384 by 384, and I resized also the 3D to the same. What's the 2.5D, in case some people they don't know what's that? The 2.5D is easily described as we took the first slice, second slice, third slice, and then we put them as one image. And then we took the second image, third image, fourth image, and then fourth image, fifth, sixth, fifth, sixth, seventh, and so on. And that's is called 2.5D images. And for the patch, we chose 128 by 128 for all images with an overlap of 75%. In UNet, we just added one more max pooling operation, as we believe the deeper it gets, the more it tries to capture the small cysts or like diseases. Um, Also for SegNet, it follows the same structure as UNet. So instead of 4, there are 5 blocks of encoder decoder. And then we didn't use the VGG16 as the original paper. Instead, we train it from scratch. Also, the deep lab, we have used it as original as it, not much of like changement. We kept it as it. As a cost function, we have used the cross entropy loss function. And then for training the deep model, we have used Adam Optimizer with initial learning rate very small, and the mini batch size was 8 volumes for 100 epochs, and images are shuffled after each epoch with 3-fold validation. The average training phase duration is 71 hours per experiment. And then for the evaluation metric, we have used the, you can say, the best metric, which is called the dice similarity coefficient. We didn't use the accuracy of all other guys, because what matters for us is to know the overlap ratio. And then the results that we got, at many places, it exceeds the human performance, but not yet enough to fully depend on it. So there is a room for improvement for people who are interested in this place or this kind of domain. So for 2D, we have tried the unit with full or with patch, and we noticed that with patch, mostly it's better. Of course, not at all levels, but like in general, it's more, it outperforms the full images. same for SegNet, and same for DeepLab. And what we can see also from 3D is really less than 2.5D and 3D in terms of performance. And this could be due to this, like the amount of data that are used. So here the input at least would be, I don't know, like around 6,000 or 7,000 images, but here the input is like around 40 or 50 because or for in this case, it's just 16 or 18, just not much. Also to be noted that 2.5D is the highest and SRF is the most recognized fluid among the other fluids. So as a summarize, we can say that the retinal fluids were better identified when patches were fitted to the deep network rather than the full image. So this could say that the overlapping patches work as a denoiser, maybe because they provide the network with more images about the same region of interest, pixels at different locations. And also we can say that the 2D and 2.5D models outperformed the 3D, and SFR fluid was the most recognized by the models. We could also say that the three models could be enhanced if more data were like more fed to the models. Um, I still believe that depth information might make more meaningful sense, but since we have lack of data, I cannot confirm that, but I have read it in a couple of experiments. For future work, we recommend using patches and maybe fuse different sizes of patches, which can track small cysts, and maybe you could use the transformers. There is a trade-off between the computation time and generating more patches to train the volume at different scales. The generated false positive could be used by applying some morphological operations such as median filter. Besides forcing the network to train, area located between the retinal layers could enhance the performance by removing the redundant or unwanted background pixels. That's all. Thank you for listening. And uh, if you have any questions, please write it for me in the YouTube link or like the place. And you can reach me out by my email or like through the YouTube, or we can have maybe a possible collaboration. Thank you.